Welcome to solverfy.
In this problem, we have light incident on a sequence of 3 different layers, each with a different index of refraction, n1, n2, and n3. These indices of refraction are given. n1 is 1.4, n2 is 1.46, and n3 is 1.75. We're also told that the thickness of the middle layer here, L, is 210 nanometers. And we're being asked, what wavelength in the visible spectrum can we shine on here such that we have minimum reflection or no reflection? So in order for that to happen, what's going to happen here is the incident ray is going to hit this first surface, and part of it's going to reflect, which is ray 1, and part of it's going to transmit, and then that ray is going to reflect off the back surface, which is called ray 2 here. In general, these rays are going to be phase shifted one from the other. If that phase shift is exactly half a wavelength, or some multiple of half a wavelength, then the 2 rays are going to cancel and you're going to have no reflection. So that means that the path length difference, or the extra distance traveled by ray 2, has to be some half multiple of the wavelength. So the extra distance traveled is twice this thickness as you go once to the right and then back to the left. So we have that 2L. The extra distance traveled has to be some half multiple of the wavelength, which I can write as lambda times m, where m is an integer minus 1/2. Right? So an integer minus 1/2 will always be a half integer. And m we start counting at 1. So 1, 2, 3, etc. And we have to be careful. The wavelength here is actually the wavelength in the material, which has some index of refraction. And that wavelength is different than the vacuum wavelength, so I'm going to label it lambda sub n, where lambda sub n is just the wavelength in the material, which is equal to the vacuum wavelength lambda divided by the index of refraction of the material. There's one more thing we have to check, because when light reflects off a surface and it's going from lower index of refraction to higher index of refraction, the reflected ray gets phase shifted by half a wavelength. So this might offset everything, so we're going to have to correct for that. So let's check. If we go from n1 to n2, we're going from lower to higher, so that means ray 1 is shifted by half a wavelength. But then when we go from n2 to n3, we're also going from lower index to higher index, and so ray 2 is also shifted by half a wavelength. So they both get shifted by the same amount, so that's the same as if there was no shift. So they cancel out, so we don't have to actually correct anything in here. We can just solve for lambda. So solving for lambda, we're going to have lambda n, which is equal to lambda vacuum over n2, since that's the material we're in, equals 2L over some integer minus 1/2. So this gives us that lambda equals 2n2 times L over m minus 1/2, and any integer value of m will satisfy this. So there's multiple wavelengths that will satisfy this, or that will end up canceling and not reflecting. But we want the visible spectrum. So we have to figure out which m results in a lambda that's in the visible spectrum. Now the visible spectrum is between about 400 and 700 nanometers. So this numerator, if we plug in the numbers, is 613 nanometers. Then we're dividing by m minus 1/2. So let's check which m's will give us a visible spectrum, or a visible wavelength. So if m equals 1, then we get 613 divided by 1/2, which gives us lambda of 1226 nanometers, which is not in the visible spectrum. So this doesn't work. So let's try m equals 2. This should work because m equals 2 will just give us, well, let's just try. We're close here, but not quite. So m equals 2 of that lambda equals 613 divided by, and now 2 minus 1/2 is 3/2. And that comes out to 409 nanometers. And that is just in the visible spectrum. Right? We said visible spectrum is 400 to 700 nanometers. So this one works. So m equals 2. And so the visible wavelength that will not reflect is 409 nanometers.